All right, what are we looking at?
If two paired dice are rolled, find the probability that the minimum of the two numbers is greater than two.
Probability that the minimum of the two numbers is greater than two, right?
Yes.
Okay. So this is a good opportunity to talk about dice in general. So when I'm rolling two dice, I generally try to think of them as being two different colors. So let's actually, we're gonna make, so you don't need to make this list every time you do this. But I do recommend, let me take around today. Fine. I would recommend being familiar with this listing process. And again, whenever I'm trying to list out the things in my sample space, so we're talking about the sample space from my, you want to be systematic. Like when we were doing heads and tails last time, same kind of idea here. So if I'm talking about rolling two six-sided dice, I'm going to think about the first die being red and it having the numbers 1, 2, 3, 4, 5, or 6. And the second die being green and also having the numbers 1, 2, 3, 4, 5, and 6. So then I would probably even make a little grid here. I know this is a long answer to your question, but I think it's worth looking at. Yeah. Oh well. So there you go. So here we have. I guess a little thing here too. So right here we have a 1, 1, and then so I'm going to write the red one first. 1, 2, or 1, 3. I guess I don't really need to write parentheses. 1, 4, 1, 5, 1, 6. And we're going to do this all the way. So I'm going to go 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 4, 4, 4, 4. All the 5s in the first spot. All the 6s in the first spot. And then across, we'll do all 1s in the second spot. This is probably the fastest way to write out the whole list. All the 2s in the second spot. All the 3s in the second spot. All the 4s in the second spot. 5s. Try to make sure your numbers don't look terrible. 6s. There is our whole list of all 36 possible ways of rolling two dice. So now the question. We want to find the probability that the minimum of the two numbers is greater than 2. And I do read that as a strictly greater than, not a greater than or equal to. So the minimum needs to be 3 or larger. So when I'm looking at the nice thing about kind of the way we did this table here is that every diagonal from lower left to upper right adds up to the same amount. So this diagonal adds up to 2. This diagonal adds up to 3. This diagonal adds up to 4. This one adds up to 5, to 6, to 7, to 8, to 9, 10, to 11, to 12. The really nice thing about drawing the table in this way. So there's only one way you don't. Anna. Sorry, I was making a mistake. I was about to make a mistake. I was about to make the mistake and say, well, all of these have a minimum that is larger than 2, except for the first one. That's not correct, because I was thinking of the sum of the 2 dice, not the minimum of the 2 dice rolled. So let me ask you all, in the first row here, what's the minimum of the 2 dice rolled? 1. How about in the second row here? That's not a good way to ask it in the second row, because in the second row, the minimum is 1 right there, and it's 2 for the rest of these. So the minimum is 1 or 2, but still not 3. So far we can eliminate all of this row, because none of those have a minimum that's greater than 2. We can eliminate all of this row, because none of those have a minimum that's greater than 2. We can't eliminate all of this row, but we can eliminate all of this column and all of this column for the same reason. The minimum here is 1. The minimum here is 1 or 2. And it looks like everything left, looks like all of that has a minimum that is greater than or equal, greater than or equal to 3 or greater than 2. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different ways we can roll 2 dice and get a minimum that is strictly, where the minimum of one of the dice is greater than 2. So if I say, and so here's some notation that is kind of annoying, but is typical. Let's say that A is the event that we get what we want, that we roll 2 dice and the minimum of the 2 numbers is strictly greater than 2. Then the probability of A is the number of ways of getting A divided by the number of ways of all the things. And typically, omega is the symbol we use for the entire sample space. Well, there are 16 ways of getting what we want. There are 36 ways that anything can happen. So our probability here is 16 out of 36, which we could reduce to 4 out of 9. That's kind of the idea here, right? Whenever you're finding a probability, the harder part is typically counting up the things that we want to count, and then dividing by the total is usually not that terrible. Yeah. I don't think there's an as effective way as doing it without drawing. Like, I'm sure we could figure it out without drawing it. I don't think it's easier to do it that way. Yeah, sorry, there's all this panel in my hand here. Okay, let me grab something real quick because yeah, I'm disappointed in myself for forgetting my notes. Oh well, I can find them on here. One moment, please. Yeah, we should start there. So let's talk a little bit about conditional probability, because we've talked a little bit about probability. The conditional probability is kind of the next thing we need to cover, because we then need to talk about Bayes' rule, which I'm sure she will ask you about on your final. Like, if I had to make a bet, I would bet a lot of money, not my life, but a lot of money, that she was gonna ask you about Bayes' formula on the final, because it's pretty standard for this class. So conditional probability. Actually, let me go back. Yeah. Sure. Yeah, we'll do that. So let's start off with this example. Number 1. In some areas of the world, about 20% of adults have HIV. 40% have tuberculosis, and 15% have both. I know, very uplifting, right? No, not really. I'm kidding. It's not uplifting at all. It's very sad. But that's not the point. This is math. We don't care about I mean, we do care, but we pretend like we don't care because you're just dealing with the math. If a person is chosen at random, what is the probability that they have HIV or TB. And so in math, when someone says or, they typically mean this or that. And then there's an implied thing that we don't say, but that is meant, or both. So when I ask the question, what's the probability that someone has HIV or TB? I also want to include the people that happen to have both. That's certainly meeting the criteria of having one or the other. We just don't say the or both part. There's another mathy thing, which we don't need to talk about, which is called the exclusive or, which is when you say, I want this or this and not both, which is kind of how we mean or in language, right? When someone says, do you want soup or salad? We don't usually mean or both. You get one or the other and not both. So our English language or is actually different than our mathematical language or typically. So when someone says or, you should think union, either one or both. So let's say that A is the event of having HIV and B is the event of having TB. And yeah, it's like I thought to stay on here, but well. So to find the probability of A union B, let's draw a little picture before we actually do it. So we often draw a Venn diagram when we think about unions and intersections. If this is A and this is B, watch for a second. I want all of A. I want all of B. But here's the problem. If I count all of A and all of B, I've counted where they overlap twice. And so I have to subtract off their overlap, aka their intersection. So this is going to equal the probability of A plus the probability of B minus the probability of A and B, or A intersect B. This is an example of the inclusion-exclusion formula, where if you're including something twice, you then have to exclude it once. In this particular example, we're going to get, let's see. So the probability of A was 40%, which is zero. Oh, sorry, probability of A was, 20%, sorry, which is 0.20. The probability of B, which was having tuberculosis, was 40%, or 0.40. And the probability of having both was 15%, or 0.15. So calculating this is going to be 0.6 minus 0.15, which is 0.45, or a 45% chance of randomly selecting an individual that has HIV or TB or both. Okay, let's look at a similar thing with Venn diagrams, just because there's at least one homework problem where I saw people are having a little bit of trouble kind of figuring out what's going on. Maybe not you all, but some people. They were given the following. We're given that A is the event consisting of the numbers, I don't know, 1, 3, and 5. B is the event consisting of the numbers, I'm sure. Well, let's make it even more. How interesting do I want to make this? Not that interesting. 2, 3, 4, and 6. And we are given that the probability of event 1 occurring is 0.15. The probability of event 2 occurring is 0.10. The probability of 3 is 0.20. The probability of 4 is 0.05. Probability of 5 is unknown. And the probability of 6 is 0.30. Then we're going to ask some questions. The first question being, what's the probability of B? Well, B consists of these 2, 3, 4, and 6, and we can certainly find those all. If I find 2, 3, 4, and 6, it's going to be, let's see, the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 6, which is just going to be 0.1 plus 0.2 plus 0.05 plus 0.30, which is something. What's like 0.65? Sure. What about the probability of A? Well, same idea. We're going to add up all the probabilities of the things inside that event, or the sample space of that event. But one of them we don't know. So before we can actually find this, right, it's going to be 0.15 plus 0.20 plus, we don't know what the probability of 5 is. We have to find that. So we have to use some of the things that are true about probabilities, which is that when you have like, if we're thinking of all of these things, 1, 2, 3, 4, 5, 6 as the entire sample space, then all their probabilities should add up to how much? Right. So we know that the probability of 5 should equal 1 minus all the other probabilities added together. And I'm just going to write out the numbers instead of writing the P of 1, P of 2, etc. So it's going to be 1 minus 0.15 plus 0.10 plus 0.20 plus 0.05 plus 0.30. Let's see, 15 plus 10 is 25, plus 20 is 45, plus 5 is 50, plus 30 is 80. So that's 1 minus 0.80, which is 0.20. So that's the probability of 5. And so that's going to be 0.20, which is going to equal 0.55. What's the probability of a complement? What is a complement? It's a good question. So whenever someone says the word complement, they mean all the things that aren't in the thing you're talking about. So A is the set consisting of 1, 3, and 5. A complement is the set consisting of everything else, 2, 4, and 6. So A complement, or more generally anything complement, A complement is the entire set or sample space minus A. And that is the correct notation for set subtraction. But some people do write it as a regular minus sign, which I think is lame, but whatever. Or if you prefer, the entire set minus A. So we take the entire set, which is 1, 2, 3, 4, 5, 6, and subtract all the elements from A. I'm left with 2, 4, and 6. That's going to be the probability of 2, probability of 4, plus the probability of 6, which is going to be 0.1 plus 0.05 plus 0.30, which adds up to 45%. 0.45. But here's the thing we should have actually done. Instead of doing all that, it is also true that the probability of A complement should equal 1 minus the probability of A. Because if you're finding the probability of everything else, and we know all the probabilities add up to 1, then the probability of A complement has to be 1 minus the probability of A. There is no other choice. So we could have easily calculated this as 1 minus 0.55, which would have given us 0.45. And that is often how people expect or encourage you to calculate probabilities of complements. Yeah, we got some room in here. Give myself a little bit more room. What if I want to find the probability of A intersect B? So this is where you can't rely on your probability formulas necessarily. It is sometimes true, although not generally true, that the probability of A intersect B is equal to the probability of A times the probability of B. And we'll talk about this a little more. Don't worry about writing down these formulas right now. That is not true here. That is true if A and B are independent, but we don't know that they are. In fact, I'm pretty sure they're not here. When you're asked to find the probability of an intersection and you're able to, the easiest thing to do is to draw it or to identify it. So you can actually look at A and B and ask yourself, what things are in both A and B? I see a thing. What is it? 3. 3 is in there, so it's really just the probability of 3, which is 0.2. If you prefer, and actually I'm going to do this because it's going to help us answer the next questions, we could have drawn a Venn diagram. We could have said, okay, there's A, there's B, and in both A and B is 3, which maybe I can make that fit in there, probably not. And then also in A are 5 and 1. And also in B are 2, 4, and 6. I want to find A intersect B. Oh yeah, it's going to be just 3. In a similar way, finding the probability of A union B, I don't really want to use the formula we just talked about on the previous page, where it's probability of A plus probability of B minus the probability of A intersect B. That formula would work, but I can also just say that A union B looks like everything, right? Literally, we're not missing anything here. So the probability of A union B is just the probability of the entire space, omega. Yes, of course. Thank you. Which has to be 1. The probability of the entire sample space is always going to be 1. Yeah. Cool. So the formulas for probability, which we'll talk about shortly here, are good, but sometimes you don't need to use them. Sometimes you just want to draw a picture and see what's what, see what's in your space, and then say, okay, well, they gave us those things, so we can calculate them. All right, let's look at, sorry, I keep having to look at my phone to look at my next example here. Okay, let's look at this example here. One more example, and then we'll talk about conditional probability and base formula. I was numbering things. Am I still numbering things? Sure. A population of cheetahs has 20 individuals. 13 of which carry gene A, while the rest, the other 7, carry gene B. DNA is taken from 5 of them. What is the probability that all 5 will carry the same gene? Ooh, good question. So very, very generally, I want to remind you, the way we calculate probability is by counting the number of things we want divided by the total number of things that can happen. So there are 2 ways we could get what we wanted. You could have the probability of all 5 having gene A, or the probability of all 5 having gene B. Now, normally, if I was trying to find the probability of this or that, like I use the word or, right? I would have to subtract off their intersection, but there is no intersection, right? You can't have all 5 with gene A and all 5 with gene B at the same time. It's not possible. So there is no intersection to subtract off. All right, so I have to calculate the probability that all 5 are gene A. Well, how many ways can I pick 5 cheetahs that have gene A? Way more than 4. How many different cheetahs have gene A? How many of them total? 13. How many ways can I pick 5 out of 13? I said the word pick, but there's another word you might think of. Right. There are 13 choose 5 ways of picking 5 cheetahs that have gene A. I can pick the first 5, the first 4 and the 6th one, the first 4 and the 7th one, and on and on and on and on and on. Right? There's a lot of different ways we could pick the 5 cheetahs that have gene A. Plus, all right, this next question should be a little easier in light of the first one. How many ways can I pick all 5 cheetahs to have gene B? Right, 7 choose 5. Okay. What's the total number of ways I could pick any 5 cheetahs? Exactly. And that's how I would leave the answer. I don't think there's any need to simplify that in any way, shape, or form, personally. And teacherly too, like not just personally, like I think for you as well, you should not simplify this. There's no value to get it. Sure. So if I was writing this on web work and not simplifying anything, the easiest way to write this, in my opinion, would be to write it as 13 factorial over 5 factorial times 8 factorial plus 7 factorial over 5 factorial times 2 factorial, all divided by, so you want parentheses around that, 20 factorial over 5 factorial times 15 factorial. Yeah, you could probably cancel some stuff. Like you could probably cancel all the 5 factorials, but this would be a relatively, I know it's too bad that it really feels like there should be like a way to write the choose function in web work, and maybe there is that we haven't discovered, but as far as I know, there isn't. So yeah, that's how I do. I should go play with that later. Yeah, I'm gonna go look for that because maybe like I know like in web work you have there's a button you can click that has like the fractions and stuff in it. Like maybe the choose function's in there. Maybe it's not super easy to get to though. So anyway, I'll go look for that later and see what I find. Ooh, also, by the way, I know this is probably not that important to you, but I just learned something really cool on Desmos. In fact, this is probably not super useful, but maybe it is. I don't know. But I want to show it to you all anyway, because I just think it's super cool. It'll only take a moment, I promise. Oh my gosh, can I get like yeah, fine. I just want Desmos. Here is something that, oh my gosh. Go away. Not you all. So here is something that is neat. Let's say you want to graph a function. You're like, okay, I want to graph a function. Let's say it's like x cubed. Oops, yeah, minus 6x squared. Nice. Well, let's say you wanted to graph its derivative and you really didn't want to find its derivative. We'll check this out. It graphs its derivative. You just write f prime of x, right? Did you all know this? No, cool. All right, I didn't either. Some student showed me that and dropping it. I was like, really? That works? That's so cool. Anyway, might be not super useful at this point since you guys are kind of done with derivatives, but maybe in your future, if you ever have to graph a derivative, now you know there's an easy way to do it. I mean, yes, also you could just tell the internet to find the derivative for you and it'll probably find it. But hey, kind of cool. All right, anyway, moving on to more just some conditional probabilities. Oh, no, he's not here. Everyone got the handout about the cards, right? Okay, cool. I have a couple extras for some people that need to get one still, but they're not here. So, oh well. Conditional probability. So here's what I want you to keep in mind with conditional probability. You're going to be given some information. That is going to potentially change the probability of some other event happening. That's the whole basis here. So for example, let's say we draw a picture. No, draw 2 cards from a deck. When I say a deck, if nothing else is said, we mean a deck, a standard playing deck of 52 cards. Find the probability that both the first and second card are hearts. And also, when you're drawing cards from a deck, we generally assume that it is without replacement, right? You're not drawing a card and then putting it back and drawing it again. Or when I'm dealing out 5 cards, I'm not dealing you 1 and then putting it back and dealing it again. So we're always thinking without replacement unless the problem specifies otherwise. So for the first card, how many hearts are in the deck? 1/4 of the deck. 13. So there are 13 hearts. So the probability that the first card is a heart is 13 out of 52. Ooh, and let me use the little notation here. Let's say that A is the event that the first card is a heart. B is the event that the second card is a heart. So the probability, so this is, well, what is it? So the probability the first card is heart is 13 out of 52. The probability the second card is a heart is going to be Well, 12 out of 51. Because there were only 12 hearts left, we drew one of them, and there was only 51 cards left to draw from. And again, this is without replacement. But I want to point out, well, okay. So this is where I should have maybe done the other way first. Okay, I'm going to come back here and we're going to take a brief detour here. Let's just answer the question like I got ahead of myself. I'm sorry. If we'd done it with replacement first, which I should have done first. So if it was with replacement, the probability of the first card as a heart is 13 out of 52. And if I put that card back in the deck and then draw again, the probability of the second card as a heart is also 13 out of 52. Which is 1/4 times 1/4, which is 1/16. I don't actually care about the numbers here. I almost never care about the numbers, really. Okay, now here's the difference. Well, so the thing is, I shouldn't be writing the probability of A times the probability of B up here because probably B should be the same, but it's a different thing, right? This is still P of A, but this is not P of B. That's not the probability of the second card as a heart. It's the probability of the second card as a heart, given that the first card was also a heart. Or in other words, it's the probability of B given that A has already happened. And that is a conditional probability. And I want to stress here, knowing that the event A has happened or transpired changes the probability of B happening. That's the whole idea with conditional probability, is that knowing some other event has taken place will change the probability of the event you're asking about taking place. Okay. All right. Notes, yes. Yeah. And sorry, the word just yeah. And you could simplify this if you wanted to. There's something weird going on here. No, that's fine. Okay, it's just weird. If you really wanted, you could say this is equal to 1/4 times 12 over 51. And they cancel a 3 here, a 4 here, and a 4 here. And 3 over 51 is 1/17. Just to point out that the probabilities are not that different from each other, but they are different. So, couple things, and here are some formulas I'm going to throw at you. So, generally, the probability of A and B isn't the probability of A times the probability of B. It's the probability of A times the probability of B happening given that A already happened. Right? If B and A are going to happen, then A needs to happen, and B needs to happen under the condition that A has already happened. And so you can write it this way. I will also point out that you could write it as probability of A intersect B equal to the probability of B times the probability of A given that B has already happened. Both of those are correct ways of writing the probability of A intersect B. Don't worry, the other formula I mentioned is going to come back up. There's just an additional thing we have to talk about before we can say it's true. Or say when it's true, I should really say. And then finally, the formula that I actually remember from both of these is if you solve either one of these for the conditional probability, you're going to get that the probability of B given A is equal to this divided by that. Probability of A intersect B divided by the probability of A. And similarly, the probability of A given B is equal to the probability of A and B divided by the probability of B. So honestly, whenever I'm thinking about a conditional probability and I say, what's the probability of A given B? This is the formula that immediately jumps into my mind. Probability of A given B is A and B happening divided by the probability of B happening. Graphically, here's what you're kind of thinking of. So if you were to think about a Venn diagram for a second, and all of this was A, and all this was B. And I wanted to find the probability of A given B. Okay, so the given B is the important part here. Given B means that we are living in this green circle over here. That's our whole entire world. That is our new sample space, as far as this question is concerned. And then what we're asking is, what's the probability of being in A, given that we are limited to this circle here? Well, it has to be all of this right here. The stuff that's in A that is also happening to be in B, because we are limited to being in B in the first place. So it really is the case that it's equal to the probability of A intersect B. I'm just going to write the same formula again. So divided by the probability of B. The little area that has both A and B divided by the larger area that has all of B. Okay. Let's look at some examples. Okay. So let's look at some examples here. One card is drawn from a deck. Of 52. Question A. What is the probability of drawing, or probability, words, that it is a queen given that we drew a face card? For those of you who are not as familiar with the deck of cards, a face card is either a jack, a queen, or a king. Those are the face cards, because they literally have faces on them in a standard deck where the drawings are what they are. So let's say that queen is event A and face card is event B. So we're really asking the question, what is the probability of A given B? And let's try and answer this in the most easy way possible before we talk about the formula here. How many face cards are in the deck of cards? How many queens are there? How many jacks? How many kings? How many total? 12. So out of the 12 possible face cards, how many of them are what we want? Right. So if someone tells you they drew a face card, you can say, well, there's a 1 in 3 chance you drew a queen. Now, we could also do this the more formulaic way, but I will tell you it is not my preference if it is easy to tell what your new reduced sample space is. Oh, that's a good way of saying it. B is the reduced sample space. It is what our new, I think of it as the whole world, right? Like whatever you're working in is your world. So in this case, our whole world was the 12 face cards. And we said, oh, what's the likelihood of getting what we want? Oh, there's 4 ways of getting what we want out of the 12 possible things in the whole new world. However, you could have also gone the longer way and said, I'm going to calculate this using the formula. It's the probability of A intersect B divided by the probability of B. All right, so what is A intersect B? What's the overlap of getting a queen and getting a face card? So this is where things are a little bit weird. It's just the queens. Sometimes A intersect B is just A, because it's essentially contained in all of B. Sometimes it's not, right? Sometimes, so your Venn, I should point out, your Venn diagram here would look like this. My Venn diagram, if this is all the cards in my whole sample space, and then here's B, set of all face cards, and here's A, completely contained in B, the set of all queens. which is definitely contained in the set of all face cards. So when A is completely in B, then their intersection, their overlap is just all of A. And that happens a lot with these conditional probabilities. Not all the time, but it does happen a lot. So here A intersect B just happens to be A. I really want to emphasize, this is not always true. Don't say that James said that A intersect B was always equal to A. Not true. It's sometimes true. But in this case, that's just all queens. All 4 queens. So the probability of A intersect B, well, how many queens are there? How many cards in the whole deck? So we're writing this as 4 out of 52. Because we're not counting the number of ways of getting queens, we're counting the probability of getting the queens, which is 4, or any queen, which is 4 out of 52. Divided by the probability of B. Well, B is a face card. There are 12 face cards, so the probability of getting a face card is 12 out of 52. It's still going to result in the same probability. I just feel like this is the longer way to do it. Now, sometimes you have to do it this way because you're not given like a physical situation where it's like cards in the deck or rolling a die or something that you know how to interpret. You're just given like the probability of A equals this, the probability of A intersect B equals that. Find the probability of A given B, and you're expected to use the formula. But if you have something where you can identify what your reduced sample space is, then I recommend thinking of it this first way. It is usually easier to conceptualize. Okay, look at some more examples here. Oh yeah, these are good ones too. So there's a lot of card examples because they're easy to do, or at least they're easy to kind of talk about. So let's look at the following. Again, we're still in drawing one card from a deck. What's the probability that the card is a heart given it is a 7? Okay, so what's my reduced sample space? And then let's say the heart is A, 7 is B. I'm trying to find the probability of A given B. So what is my reduced sample space? Right, but so that's the number of things in the reduced sample space. Sure. What are the things in my reduced sample space? You could say all the 7s. So the 7 of hearts, the 7 of clubs, the 7 of diamonds, and the 7 of spades. So there's your reduced sample space consisting of 4 things. Although I like your answer, Tels. I'm like, yeah. So we know we're trying to find the number of ways of getting what we want out of the total number of things possible. Well, there are 4 total things possible, and how many of them are what we want? 1. There's 1 heart that happens to be a 7 out of the 4 7s total in the deck. Or we could have done this the other way. The probability of A given B is the probability of A and B divided by the probability of B. The probability of A and B. So this is a case where the overlap doesn't consist of all of A or all of B. Right? All of A is all the hearts. How many hearts are there? 13. And B is all the 7s, and there's 4 7s. But the overlap isn't all 4 7s or all 13 hearts. The overlap is literally 1 card, the 7 of hearts. So the probability of A and B is 1 out of 52. The probability of B, which is the probability of drawing a 7, is 4 out of 52. And as is expected, the probability is the same calculated. Either way you calculate it, you should get the same answer. And so we definitely get 1/4 here because those 52s cancel out. Nice. Let's see. Yeah. So just as a, I'm going to point something out here real quickly. Just as an extra question here. What's the probability of getting a heart? I should say, what's the probability of A? Not. Just very broadly, like no conditions. What's the probability of getting a heart? Right. Or if you prefer, 1/4. we're gonna use that in a minute. Let's do one more example like this, and then we'll talk about something special. So what's the probability of a king given that the card is a club? Well, same idea, except kind of reversed. King is A, club is B. Probability of A given B is going to be, well, our whole world B consists of how many cards? 13 clubs. How many cards are there that are a king and a club? 1 card. 1 out of 13. And yes, we could also do it the other way, but I don't think we need to. I will also point out here that the probability of A, which is the probability of getting a king, is the same. It is equal to 4 out of 52, which is 1 out of 13. And there's a reason I'm pointing this out. The reason is, yeah, I'm just gonna say this now. The reason is that these two examples here are examples of events that are independent of each other. Events are considered to be independent if knowing that one of them has happened doesn't change the probability of the other one happening. So in both of these examples, events A and B are independent. This is not at all the same as being mutually exclusive. In fact, it is true that if two events are mutually exclusive, they are not independent. So events A and B are independent because we can see that the probability of A given B is the same as the probability of A. Or in other words, knowing that B has happened doesn't affect the probability of A happening. Knowing B happened does not affect the probability of A happening. That is the very definition of two events being independent. One of them could happen or not. We don't care. It doesn't affect the probability of the other one happening. And then I will just point out, because I do think it's worth knowing, that that's the same as saying the probability of, well, I need to write it down. I shouldn't just say it. Let me write it down. So let me say one more thing about that. So independence. I always want to think of it that way because it feels like it makes the most sense to me. Right? Probability of A given B equals the probability of A. That is my preferred way of stating / showing that two events are independent. But it's not the only way. So let me show you how else we can rewrite this. So you could also rewrite this as, well, the formula for the probability of A given B is the probability of A intersect B divided by the probability of B. And if we're saying that's equal to the probability of A, then we can take this equation and multiply both sides by the probability of B to get the probability of A intersect B is equal to the probability of A times the probability of B. Or in other words, if A and B are independent events, then the probability of A intersect B is equal to the probability of A times the probability of B. And vice versa. If these two things are equal to each other, then you can automatically deduce that A and B are independent events. You can't have one without the other. So when people try to show something is independent, they either try to show that these two things are equal or that these two things are equal. And either way is fine. I like this because I feel like it is more meaningful, but this is also true. Okay. Okay, let's see where we're at. All right. What time? What time is it? Oh, yeah, okay, we got, yeah. Yes, okay. We'll do one more example and then we'll do lots more examples. We'll do one more example and then we will talk about a special thing called Bayes formula. Although we won't really talk about the formula per se. Don't worry. Let's look at this example. A multiple choice test has 10 questions. Each with 5 possible answers. A, B, C, or D, or E. Find the probability of answering all 10 questions correctly by randomly guessing. First of all, it doesn't seem like it's going to be very likely, right? If you were to guess on all 10 questions of a multiple choice test like this, where you had 5 possible answers. No, in fact, even if there was only 2 possible answers for each question, the probability of getting all 10 right would be 1/2 times 1/2 times 1/2 times 1/2 times 1/2, 10 times, which is 1 out of 1,024, or less than 0.1% chance of guessing all 10 correctly. And that's only with 2 different possible answers. Let's see what it's going to be for 5. So, yes. So the probability of all 10 being correct. So I will point out, mathematicians are lazy. I could have written A is the event that all 10 are correct, or A is the event that one of them is correct, and then did P of A, but we're just going to write the thing we want. So what's the probability of guessing the first one to be correct? Right. What about the next one? What about the next one? Right. They're all 1/5. So the answer is going to be 1 out of 5 to the 10th. Which, if you plug that into your calculator, you get about, what is it here? 1.024 times 10 to the -7th. Very, very unlikely that you're going to guess all 10 correct. And you can have people like do like the brackets for, what was it, March Madness? Like fill them out and they talk about like how there's like, if you give each team a 50-50 chance of winning, like no other knowledge, chance of getting all 64 games correct or whatever is like 1 out of like 500 quadrillion or something. Like it's so infinitesimally small. Now, granted, you could better your odds by making logical choices and thinking about like, well, this team is favored, but still, I don't think it's ever been done, right? Like it seems very unlikely. Okay, here's a more interesting question. Probability of getting 9 out of 10 correct. So, how many different ways can I get 9 out of 10 correct? You might think 1, but no, I can get the first 9 correct, or the first 8 in the last one, or the first 7 in the last 2, right? Basically, it's the probability of getting all but the first, and all but the second, and all but the third, all the way to all but the 10th. Or in other words, how many ways are there of choosing 9 questions to be correct out of 10 possible questions? 10 choose 9, which is equal to 10. Right? Because we're just choosing the one that we don't want to be correct. And there's 10 ways of choosing one thing out of 10 things. Okay, so now, if we want one of them to be not correct, the probability of one of them being not correct is not 1 out of 5, it's 4 out of 5. Right? Because if you're trying to get it wrong, I mean, you're not trying to get it wrong, but we're going to say one's wrong. There's a 4 out of 5 chance of one of them being wrong. And then if the other 9 have to be correct, that's going to be 1/5 to the 9th power. That's the probability of getting the first one wrong and the other 9 right. And then the probability of getting the second one wrong and the other 9 right is also 4/5 times 1/5 to the 9th. And it's the same probability for all 10 of these. So here the answer ends up being 10 times 4/5 times 1/5 to the 9th. Which is very small. Not quite as small as getting all 10 correct, but still pretty small. And so do any of you still have to take stats? Okay, so when you get to the binomial distribution, you're going to be seeing this. This I would write out as this. It is 10 choose 1, because I want, sorry, 10 choose 9. I want 9 successes. And then it's my probability of success to the 9th power times the probability of failure to the 1st power, because I want the probability of success raised to the number of successes power and the probability of failure raised to the number of failures power. You will definitely see this when you take stats, when you talk about the binomial stuff. Okay, we got time. All right, cool. So now, oh yeah, question. So, and that is one of the harder parts for sure. So the general kind of rule I keep in mind is when it's an and, we want to multiply. When it's an or, we want to add. So here, and actually this is a really good example of it. So when I said I want probability of 9 out of 10 correct, I want the probability that the first 9 were correct, or the first, oh my gosh. All right, let me just read this one. The probability that not the first one was correct, or the probability that not the second one was correct, or the probability that not the third one was correct, or all the way here. And then when I was calculating the probability of the first one being correct and the other 9 being, sorry, first one being incorrect and the other 9 being correct, there's an and. So the probability of the first one being incorrect is 4/5 and times the probability of the other 9 being correct, 1/5 of the 9th. Or the second one's incorrect and the other 9 are correct. Or. So that's kind of the idea. I know it is not very spelled out, right? It is just kind of something, I say this, unfortunately, you kind of have to develop a feel for. But with practice, you can develop a pretty good feel for, like, oh yeah, we want this thing to be true and this thing to be true at the same time, versus, oh, I'm looking at this whole situation being true, but I also want to add on this other thing where this other thing can happen, like the probability of 1 being correct, or the probability of 2 being correct, or 3. I know that's like what we just talked about, but yeah. So practice is kind of the real answer. Oh yeah, let's go there. All right, so here is the lead up to a base formula question. So what do we have here? A blood test for a disease shows a positive result in 98% of the cases when the disease is actually present. Or in other words, which we'll write down in a second, the probability of a positive test given that the person has the disease is 98%. So the words I've just written down there are a conditional probability, right? The test is positive 98% of the time that the disease is present. We're not saying the test is always 98% positive, right? That'd be weird. It's 98% positive if the disease is there, which is good. Okay, more information here. In 6%, oh, sorry. Let me say this the right way. The test also shows positive in 6% of the cases where the disease is not present. A false positive, right? You don't have the disease, but you still tested positive. Assume that the prevalence of the disease is 1 in 250, or 0.4%. So now we're gonna ask some questions. So question 1. If a random person is given the test, so we don't know if they have the disease or not, which is typical if you're testing someone for a disease, right? You're testing them because you don't know if they have the disease or not. So if the random person is given the test, what is the probability that they test positive? Okay, so let's write down a few things before we try to answer this question. So I'm going to say that A is the event of, yeah, sure. A, I have to use D, whatever. A is the event of having the disease. And instead of saying B is not having the disease, we should say that A complement is not having the disease. Does not have the disease. And then it is pretty standard to, instead of using B and B complement for a positive or negative test, we just use a plus and a minus sign for a positive and negative test. So the plus is going to be a positive test, and the negative is going to be a negative test. And let's actually write down what we were told as well. We were told that given the person has the disease, there's a 98% chance of them testing positive. So the probability of a positive test, given that they have the disease, is 98%. Just so you make sure you're reading this correctly, the second thing is always the given piece of information. Similarly, the probability of a positive test, given that they do not have the disease, we were told that it was 0.06. And finally, or thirdly, the probability of having the disease is 1 out of 250, or 0.04. That's not right, 0.004. Sorry, 0.4% is 0.004. The way I'm thinking about it really is, I know that 1 out of 25 is 4%. So 1 out of 250 is 1/10 of that. Okay, there are lots of formulaic ways you can deal with this, but I'm going to tell you, in my opinion, the easiest way to handle the situation. So whenever you see like wording like this, if you see wording like this where it's, we know the probability of testing positive given that you have the disease is whatever, we know the probability of testing negative given that you have the disease is whatever, or something else like that, you want to draw a tree. Or a tree diagram. Like, draw a tree, like, draw a tree diagram. Tree diagram is the way to go. So here is our tree diagram. At the first juncture, you have two choices. You can either, or the person can either have the disease or not. One of those two things has to be true, right? For everyone, right? They either have this thing or they don't. What's the probability that they have the disease? 1 in 250, or 0.004. So this probability here, the probability of A is 1 in 250. Okay, if you know the probability of them having the disease is 1 out of 250, what's the probability that they don't have the disease? Right, 1 minus that, 249 out of 250. Great. Now we branch. Say, okay, well, if you have the disease, there are two possible things that can happen when you test. You can either test positive or test negative. Given that we're along this branch, given that we have the disease, what's the probability of testing positive? Thank you. And by subtraction, what's the probability of testing negative? Right, you don't have any choices here. That's got to be 0.02. Because every branching, all the branches have to add up to 1, or 100% probability. Same deal down here. Given that you don't have the disease, what's the probability of testing positive? Right, And so then the probability of testing negative has to be 0.94. Okay, now to answer the question, which I know you can't see anymore. If we pick someone at random, what is the probability that they test positive? Well, I want to find all the paths that get me to positivity. So the probability of testing positive is equal to all the paths that end in positivity. How many paths get me to positivity? Well, I can either go along this path and have the disease and then test positive, or I can go along this path. Oh, notice I said or. So I can have the disease and test positive, or not have the disease and test positive. That should completely spell out to us what we need to multiply together, what we need to add together. So it's really important when you say these things and write these things down that you pay attention to the words you were saying in your head. So this is going to be the probability of having the disease. I don't actually need to write this down, by the way. You don't, what I really should say is you don't actually need to write this down unless you want to. But what I'm pointing out is that we know what these are going to be. It's the probability of A times this probability here, which is the probability of not a positive test, but a positive test given that we tested positive or that we have the disease. Sorry. Or the probability of not having the disease times the probability of a positive test given that we didn't have the disease. I should point out, just so you all can see it, that this is just the probability of having the disease and testing positive. This is just the probability of not having the disease and testing positive. This is the idea, or what's called the law of total probability, where if all my negatives over here, and all my positives over here, and this circle is all the people that have the disease, and everything outside of it is the people that don't, then here is, in red, A intersect the positives, and here in blue is A intersect the negatives. And together, that's all of A. Except I didn't want all of A, I wanted all of, I fucked it up, sorry. Should have, I got the A and my plus backwards. This should have been the plus. Let me draw it again. Sorry, I was trying to say something cool and sorry, what I should have said is, here's all the people that, yeah, sure. Here's all the people that have the disease. Here's the people that don't. Although that's not, my sizes here are not representative of the actual numbers. That's okay. And here's the people that are testing positive. So here are my A and positive. And here are my A complement and positive. And together they give you all of the positives. Sorry. Okay. You don't actually need to know that either, though, because really, if we just look at the tree, we can say, okay, well, the probability of being positive is going to be this times that. Plus this times that. And that's it. Relatively not terrible to calculate. It ends up being approximately 0.0638. Which makes sense if you think about it, because what we're essentially saying is the probability of testing positive is about 0.06, which is really the probability, which is very close to the probability of a false positive. Which makes sense because so much of the population is negative that the majority of positive tests we're going to get are coming from the false positives that we get from all those people that don't have the disease. So that's why our probability of a positive test is very, very close to the probability of a false positive test, because there's such an overwhelming majority of people that don't have this disease. And that's pretty typical in general for these kinds of problems. So I want to answer that, but that's not that. So let's get to the so we'll get to the base formula part here, which is kind of cool. So Usually this whole setup is in the guise of trying to answer the question, well, I know the probability of a positive test, given that someone has the disease, is 98%. But that doesn't help me because I'm not taking the test because I know I have this disease. I'm taking the test because I'm wondering if I have this disease. So the question that we really want to answer is, what is the probability of having the disease, which I remind you is event A, given that we had a positive test? So instead of trying to find the probability of A given a positive test, which we were told was 0.98, that's not what we want, although we're going to use it. What we want is, we want the probability of a positive test given that, wait, did I say the wrong thing? Sorry, I did. Sorry. Let's go back and look, just so I can make sure I'm not saying something incredibly stupid here. We know that the probability of a positive test given, I wrote the wrong thing for sure. Right, we were told the probability of a positive test given that they have the disease is 90%. And I wrote the very wrong thing here, which I'm very sorry for. That's what we're trying to find. So we want to find the probability that we have the disease given that we have a positive test. That is what we are interested in knowing. And again, this tree diagram is going to help us get there. So here's what I would say about this. We need to be able to, in my opinion, always go from this conditional probability to the nice version of it that I like, which is what everyone likes. That the probability of something given something else is the probability of their intersection divided by the probability of the given thing. But again, the tree will get you there. The tree is wonderful, in my opinion. It is I know it sounds a little bit like the tree is really great. So let me ask you all, how many paths are there that get me both having the disease and a positive test? One path. And it's the path that starts with having the disease and then moves to having a positive test. So the way of having a disease and a positive test is going to be 1 out of 250 times 0.98. How many ways are there of having a positive test? Well, we actually just answered that question, but there's two paths, and the paths are going to be that times that branch times that branch, 1 out of 250 times 0.98 plus that branch times that branch, 249 out of 250 times 0.06. And if we want to calculate it, because I kind of do want to calculate it to know what the answer is. And then I bring my calculator. It's terrible. Well, it's okay. I can do this there. I mean, it's going to be a slight approximation, but we'll live with it. Let me see if you can beat me to it. So it's 0.0638 plus. Sorry, you guys are probably faster than that. Phone calculator is going to kill me. No, it's all right. That's all right. So we're getting approximately 0.06772 divided by 0.06772 plus 0.0638. And if we do that, I can have a pretty good food. 0.0638 equals, and then so it's going to be 0.06772 divided by 0.13152, which should be about a half. Yeah, it's about 0.5149. In my opinion, and most people's opinion, very contrary to what people usually think. People often think, oh, if there's a 98% chance of having a positive test, given that I have the disease, then there should be about a 98% chance of having the disease given a positive test. And clearly, from the work we've done here, that is not true. Given a positive test, there's only like a 50% chance of having the disease. And that's a phenomenon that generally occurs with this, right? Is that the conditional probabilities don't match up when you switch the direction. They are very different because of what they depend upon.